Okay, we're recording.
Okay. Hello, everyone. It is my great pleasure to introduce Andrea, who's going to be talking to us about machine learning techniques for predicting the geoeffectiveness of coronal mass ejections. So Andrea is a 24-year-old computer science graduate from the Technical University of Cluj-Napoca in Romania, and she has started working on this research project as part of her bachelor thesis after she discovered me on the internet by pure accident. So she is currently pursuing a computer science master's at the University College Dublin in Ireland, and she is also working part-time as a machine learning engineer. So Andrea, you have the floor.
Hi, everyone. Thank you for having me today, and thank you for joining my presentation. Before we begin, I'd actually like to extend special thanks to Dr. Paraskiv, because though he may be too humble to admit it, none of this would have been possible without him. This being said, today we're going to talk about machine learning for predicting the geoeffectiveness of CMEs, as Aline has already told you. This is based on the work behind a paper that I've authored together with Dr. Paraskiv, Dr. Bashliu Ionescu from the Astronomical Institute of the Romanian Academy, and Dr. Marginan from the Computer Science Department of the Technical University of Cluj-Napoca. Today, we're going to go through a brief introduction of the context. We're going to cover the algorithms that I've used. Then we're going to talk about the context-specific challenges that I faced and the approaches I've experimented with to tackle them. And finally, we'll discuss the results and their interpretation. As I am sure that you have significantly more knowledge in the solar aspects of this work, I'll focus mostly on the computer science part, but nonetheless, some definitions are necessary. And so by CME, we mean coronal mass ejection, which is a solar eruptive event that can cause geomagnetic storms, meaning it can be geoeffective. And by geoeffective, we mean associated with the DST index value lower than or equal to -30. The goal of this work was to find an automated method to answer this question. So given some solar onset numerical data that defines the CME, we want a machine to be able to tell us whether the CME is potentially geoeffective or not. And you can see here that I've highlighted solar onset parameters only, and this is because this would ensure that we have the maximal warning time in case there is a potentially geoeffective CME. If we used interplanetary data, would restrict the warning times to only a few hours. So we believed having a more generous time frame would be better, and thus this model could be used as an initial filter. For the dataset, we've used 4 different features from the LASCO catalog that I'm going to show you in a second. And since there's only 4, and that's very little, I've tried to add as much data as I could. Unfortunately, that only meant 1 more feature, which is a flare index that then again, unfortunately, was only computed up to 2015. So we had to restrict the data from LASCO to the end of 2014 as well, so as to have this flare index as well. And while these are the inputs, we needed to know which CMEs were geoeffective and which weren't, and we've obtained this data based on the DST correlations from the Richardson and Kane catalog. This is a screenshot from the LASCO catalog, so if you go there, that's what you see. And these highlighted in green are the features that we've used for the model. So we've used the central position angle, the angular width, the linear speed, and the acceleration. We couldn't use the mass and the kinetic energy because these the values are missing for most of the samples. And we didn't use the other data available because these are correlated with the features that we're already using. So having them wouldn't bring any plus. And the initial experiments showed that these performed better than, so the linear speed performed better than the other speeds, and the CPA performed better than the MPA. In terms of distribution, we can see that there's an overwhelming majority of non-geoeffective samples and a very small fraction of geoeffective ones. So we've got the data, we've got the question. We now want a model that will tell us whether the answer to this question is yes or no. And because machines and computers in general prefer numbers to text, what this model would do is it will output a 1 if it believes it's geoeffective, or a 0 otherwise. So what this model is basically a binary classifier. And I'll take you now on a whirlwind tour through the methods that I've used for this binary classification. The first one, and probably the easiest to understand, is a logistic regression. So we're basically just trying to find the curve that best separates the two classes. What we're using is a linear regression with an additional sigmoid function. And this function basically ensures that the outputs are between 0 and 1, and thus we can interpret the result as a probability of the sample belonging to the positive class. By positive, I mean 1, and therefore geoeffective. We're going to cover the performances and performance metric later on, but it will be useful to keep in mind that this one performed the best in terms of recall, so in terms of one of the performance metrics. Another classification method that we've employed was k-nearest neighbors, and I usually like to think about this as the mathematical way of saying birds of a feather flock together. So given a data sample, we can imagine it as a point in an n-dimensional space, where n is the number of features it has. And we can usually assume that similar data samples or similar points will be closer to each other. And thus, if we want to find the label or the class of a new point, what we could do is see how far from the label one is and how close to a cluster maybe it would be. Or in other words, we would compute the distance from this sample that we want to label to all the other samples in our data set that are already labeled. We would sort these distances and take only the k smallest ones. And then we would look at the labels of those k nearest neighbors. So if the majority of them would be purple in this case, we would say probably this new point is purple. If the majority of them would be geoeffective, we would say they're geoeffective. Similarly, as I've said, we're going to talk about the performances later, but this one performed best in terms of precision. And I'd like to point out here that while the machines do in fact do the heavy lifting or the computational heavy lifting, the job of the developers or the machine learning engineer is to experiment with all sorts of stuff that would make those algorithms better. And I've chosen to go a bit into detail with the k-nearest neighbors just so you can get the flavor of what is done behind the scenes, because this is usually the simplest to visualize. One example of experiments that we perform in this case is what kind of distance should we use? Should we compute the distance as a Euclidean one, as a Minkowski one, as a Manhattan one? Then we need to find out what is the best K for this problem and experiment with uniform weights. So simply simply using a majority vote for distance-based weights in which the labels of closer neighbors weigh more than the labels of neighbors that are farther. And I'd like to show you a little visualization so that you can get a taste of what these hyperparameters can do. So we usually need an odd value for K because, as I've said, we need to have a majority. But starting from that, we might have 3, and thus, in this case, we would label this new point as red, or we could have 5 or more than that, and in this case, we would label this point as purple. And when we find the right number of K, we would then ask ourselves whether these neighbors should weigh the same, or whether maybe these 3 neighbors that are closer should weigh more. And this is particularly important in data sets like this, where we have few samples from a certain class. And these exploration becomes even more important because the majority class will tend to be overwhelming and overpowering and control the computations. Another method that we've employed was support vector machines. And this is an algorithm for finding the optimal separation hyperplane between classes. Simply put, before we think about hyperplanes, I usually like to see what happens in a 2-dimensional hyperplane. And so we need a separation between 2 classes. Very simply, we could have a linear separation, but even so, there's very many ways, as you can see, in which we can draw a line to separate those classes. And the question becomes, which is the best line that separates these 2 classes? And this algorithm says that we basically need to find some defining points that are the support vectors, and then find the maximal distance between them and draw a separation that ensures these support vectors are as far from it as possible, because the distance from the separation line can be interpreted as a confidence. So it's usually harder to distinguish between classes when they're close to each other, these points that are close to the separation, but we're more confident that a point belongs to one class or another when they're farther from this, this separation. Sorry. But that's the easy case when there's a linear separation between the data. However, that's not always the case. But support vector machines employ a mathematical trick called the kernel trick, which uses a kernel function to take the data into an n-dimensional space where it can be separated by a simple surface. And the kernel, for example, is one of the hyperparameters that we need to experiment with when we're using support vector machines. The other algorithm that I've used to try to find the best binary classifier was artificial neural networks. And an artificial neural networks is just a system that learns a function that best maps the inputs to the outputs and has this specific structure of fully connected layers that contain neurons. And in order to understand how this works, it's best to look inside a neuron and see what it does. In each neuron, the inputs, either the actual inputs in the first layer or the outputs of the previous layers, are multiplied by weights. So each connection has its own weight. which are then summed, and there's a bias added. So far up to here, we only have a linear regression in a neuron. But if we only kept it as a linear regression, then we'd only have very simple linear functions in the end. And in order to add complexity, this linear function goes through another additional function called the activation function. And there's some activation functions that are commonly used, like the sigmoid, the hyperbolic tangent, the rectified linear unit. And this is basically what adds the complexity. And if we extrapolate what happens inside a neuron, then we've got how the neural network works. However, I feel like they're still considered such a black box that I think we should go slightly deeper into how do neural networks learn, what happens during the training, or more generally, how do machine learn? And this is going to be useful as well when we're going to talk about the challenges that we've faced. So we have the task of predicting a value that's as close to the actual value as possible. Or more formally, we need to find the function that models the data best. And finding a function simply means finding its parameters. In the simple case of a linear regression, it would mean we need to find the weights and the bias. And the way we do this is by reframing this problem as an optimization problem. So we need to define an error, and this is a bad kind of function in terms of optimization problems, but it works for this simple explanation. So we need to define the error of our model, which can be the difference between the actual output, what we really want to obtain, and what we obtain in fact. And at first, models start with random values. They make a prediction based on those random values. Then we compute the error. And what happens next is we need to tweak the parameters of the model with respect to that error in order to minimize it the next time. So some of you might be familiar with this as an optimization problem or with the terms of gradient descent, where we're trying to go down a slope to find an optimal minimum, ideally a global minimum. So we're tweaking these parameters, and then we make a new prediction, and this repeats until we either have a sufficiently low error or for a predefined number of steps. And with this in mind, I hope that you will be able to see how this applies to a neural network. So we've got the inputs, the computations happen neuron by neuron, we get the prediction, we compute the error, and then we update each weight. And that's it. This happens multiple times until we've got the perfect or the best weights we could get. And while this is quite complex, we still didn't get satisfactory results. And this is the point where we've said, well, we've got a model that has good precision and we've got a model that has good recall, so why not combine them? And thus, we've created an ensemble model, which was the best performing one so far. And the way we combine the predictions of each of these models is by using an additional model. And I've chosen a simple one because it performed well enough. And so we've got another linear regressor that's trained to learn how to best combine the outputs of these two in a single prediction. And as I've said, this one worked best, however, not with additional tweaks. not without additional tweaks. And so we're going to go into the challenges of this this task. And by far the most pressing one, at least at first, was the fact that there's an extreme imbalance between classes. So over 99% of our data was non-geoeffective samples. And another issue that we've identified was the fact that in the Richardson and Kane catalog, there are some samples, some geomagnetic storms that are not associated with a specific cause, which can be either because CMEs are not the only potentially geoeffective event, so they might not have been caused by CMEs, or because it couldn't be established clearly which out of multiple CMEs could have been the cause. But we're first going to talk about what we did about the class imbalance. And we've applied 3 different techniques. One of them was trying different class cutoffs. The other one was trying to give more importance to minority class examples. And we've also used resampling. So we wanted to have more data from the minority class and less data from the majority class. And for this, we've generated some artificial samples. But first, let's talk about the class cutoff. If you remember, I said that some of the models would output a value in between 0 and 1 that could be interpreted as a probability. And usually, we would consider all the values higher than or equal to 0.5 as indicating that the sample should belong to class 1. However, we experimented with higher thresholds, and the results improved significantly after the 0.7 threshold, and even for 0.9. So the precision increased when we told the models only output 1 if you're more confident than, let's say, 50%. Then, as I've said, we've tried to give more importance to samples from the minority class. And this is where this integrates with how machines learn. Using the weights basically applies at this point in the training. And what happens is we're multiplying the error by a weight. So we're making higher, more significant changes based on the errors made on data set samples that we're going to see less frequent, so from the minority class, and we're making smaller changes for data that we're going to see frequently because, well, we've got many samples to learn from, so it's all right to make small changes. And the way that we need to multiply is basically inversely proportional to the class frequency. So if the model performs well or bad on a class that's infrequent, it will be penalized or worse. And I think it's better if I try to explain this in with a small exercise, so to say. So please imagine that us as humans would have to learn how to solve math exercises in general based on this limited amount of data in a limited amount of time. So we have multiple easy samples and a hard example. And we know that in the exam, we're going to be tested on the hard one. So we could think of how much effort to put or how much time to put into learning each type of exercise by computing a weight for each class. And in this case, we can see that we have 4 samples. 3 of them are easy, 1 of them is hard, and there's 2 classes, easy and hard. So we could say spend 2 minutes or 2 hours on this extra hard problem, but spend less on the easy one. So if you made a mistake when trying to understand the first one, it's all right, only spend little time on this. You're going to get more samples like this so you can practice. But if you made a mistake on this hard one, do spend time or do make changes to your approach now, because you won't see many other examples like this. And finally, as I've said, we wanted to use resampling, which is very common in cases where we have imbalanced data sets. Usually, this involves random undersampling and oversampling. By undersampling, we mean we randomly remove some of the samples from the majority class, whereas by oversampling, we mean duplicating some of the samples that we already have. However, that wouldn't differ much from the class weight, so it would simply be seeing the same data more times, which is similar to giving it a higher weight. And so we wanted new data. For this, we've used a technique called SMOT, which means Synthetic Minority Oversampling Technique. And I'm going to try to explain how it works on this example toy dataset, where the minority sample that we want to create more samples of is the red one. The first step is to select one point at random. Then we're going to select k of its nearest neighbors, and only for simplicity, I've chosen k equal to 2 here so we can more easily visualize this. Then again, because we believe that points that are closer together are probably more similar. Then out of those k, we only select one neighbor at random. And on the line between the initial point and one of its closest neighbors, we simply at random generate a new point. And this is our new data sample. Do you see any issues here? Well, the main issue is the fact that at no point was there any attention paid to the majority class. For all we know, this point could very well be overlapping one of the existent points from the majority class, which, as you will see soon, is a real problem in our case because we've got many overlapping points already. And what this would mean is that you create a new data point that has the exact same features as a point from a different class. So you're giving the exact same data to your model and you're saying it has label 1 now, but it has also label 0 now. However, this did lead to some improvements on at least 2 of the models, one of them being the neural network, showing that having more samples from the minority class could improve the performance. And now back to the other problem, which was uncertainty. As I've said, there were 131 geomagnetic storms in the Richardson and Kane catalog with no clear CME associated, either because the cause was not the CME or because it couldn't be determined which CME was the cause. If we think that it could have been a CME, but we just couldn't figure out which one, then it means that we are now training the model on some samples that actually were geoeffective. We're telling the model that they were not and expecting good results. And in order to mitigate this possibility, we said, let's look at these 131 geomagnetic storms. Let's take all the CMEs from 15 hours before up to 5 days prior, which is the time frame in which a CME could have caused this geomagnetic storm, and let's assign half a weight of the majority class to these samples, so that in case the model makes a mistake, it's not going to be penalized as much. So in case the model says 1 and it's actually a 0, we're not going to make such a big change. We're not going to penalize it as much because us as humans wouldn't know if it was a 1 or a 0 either. So in order to mitigate that issue, basically, we're simply giving less importance, let's say, to that when it comes to training. And finally, the results. We've obtained 96.66 accuracy. Is that good? Is that bad? Well, if we think that in this specific case, if a human or a model would simply always say non-geoeffective, no matter the inputs, they'd be correct in 99.3 of the cases. So they'd have 99.3 accuracy, which is the reason why in cases of imbalanced data sets, accuracy can be deceiving standalone, and it should always be presented together with other matrices. So what matters in our case? Well, we care about how many of the geoeffective events we can identify, which is formally known as the recall or the hit rate. And we also care how much we can trust that when the model says geoeffective, the CME is actually geoeffective, which is the precision. And these are the results. So we can identify almost 80% of the geoeffective events. Now, then again, is this good? Is this bad? Usually visualizations help. So it would be very useful to see the data and to see our predictions. However, we've got 5 features, so our data has 5 dimensions, and us humans can only perceive visually well up to 3 dimensions. So we needed to map the data set to a lower dimension. And for this, I've used UMAP, or Uniform Manifold Approximation and Projection, which then again was used for the dimensionality reduction for visualization purposes. This is similar to principal component analysis, but works well for nonlinearity as well. Also similar to t-SNE, if you're familiar with that. As I've said here, it's a math-heavy new method that I've referenced at the end of this presentation if you want to learn more. The gist of it, then again, is that it takes our data and it transforms it into a 2D representation so that we can assess it and analyze it visually. And here is the result. Here is our data in 2D, colored by the prediction. This is the test set only. So 20% of the data was at first set separately. The model has never seen it, and it's only being tested on it. So you can see here that there's a vast majority of true negatives. So we're correctly identifying many non-geoeffective events. We have a few false negatives. So these are some geoeffective events that we're not identifying. In green, you can see the true positives, so the events that were geoeffective and we've correctly predicted them as geoeffective. And with yellow, you can see false alarms. If we remove the true negatives, we can focus better on this. And you can see that there's the false alarms look like a little curve here. And if we look at the entire data set, colored by whether it's geoeffective or not, we can see that the geoeffective samples actually do form some sort of a curve here, and there's some others scattered around, which is what the model picks as well, that the curve here should be geoeffective and there are some other scattered around. And so if in fact there is a curve of geoeffective events here, how come these are all false positives? And if you remember, I've mentioned this before, overlapping is a big issue in our data set. In fact, after we've mitigated the extreme imbalance issue, this is the next biggest issue. The fact that most probably we do not have enough data to distinguish well between geoeffective and non-geoeffective samples. Meaning a CME that's geoeffective or not could look very similar in terms of the parameters that we're using. So in terms of CPA, acceleration, angular width, linear speed, they could be very similar, and they are very similar, and you can see that they're overlapping. So underneath the red geoeffective dots, there's purple non-geoeffective ones, which is why these are all false alarms and not actually positive. And the curve here, moreover, is caused or is represented by HALO CMEs, or CMEs that have the central position angle and angular width both equal to 360. In other words, what the model learns is that the HALO CMEs are most probably geoeffective, which is in accordance to the belief that they are the most geoeffective types of CMEs. But as I've said, it is very likely that we do not have enough parameters to distinguish well between geoeffective and non-geoeffective samples. And one example of a feature that could help us better distinguish between classes is whether the CME was front side or back side. So whether it was directed to Earth or not, as literature shows that it is highly unlikely that a backside CME would be geoeffective. And this is just one example of an additional feature that could help distinguish better. In summary, we believe that the recall is the most important performance indicator. So the amount of geoeffective CMEs that we can identify and correctly label as geoeffective. And we've obtained a value that's almost 80%, which is good for an initial filter if we think that we're only using solar onset parameters. So this ensures enough time to better filter the false alarms with interplanetary data, for example. And from the precision issue, what we can see is that this reinforces the fact that HALO CMEs seem to be the ones with the highest geoeffective potential. And we can also conclude that most probably there are other features that make the difference between geoeffective CMEs and not. This being said, thank you very much for your attention, and I would be very glad to answer any and all of your questions.
So, can you hear me okay?
Yes.
Yes, so if you go back to your figure that has, the blue cloud and then the red curve, that's the one, yes. So can you give us some idea of what the X and Y axis are representing there?
Unfortunately not. So this is the
That's what I was afraid of.
the 2D representation of our data. We might as well ignore the axis values.
Well, it's not so much their values, but there's clearly a red curve then connecting some things. And so usually when I think of a red curve, a curve in a two-dimensional space, I'm imagining that it says that the X is related to Y by some function. This is my simple-minded picture. But if I don't know what X and Y are, then I don't know what that curve is showing.
I do understand that, but then again, true analysis of filtering the data and looking at what these red values are, this curve is formed by those CMEs that have the central position angle and angular width equal to 360. So those are basically here with some variation, of course. But if these two parameters are equal to 360, then they're most probably on this curve.
So it's not only the 360 ones that make the curve, but all the 360 ones are on the curve.
Yeah.
So there's the plage is higher than that. The problem with this is that we are plotting 5 or 6 dimensional data and we want to put it on a 2-dimensional so that we can understand. And that's why the axes don't mean anything. It's the combination of a subset of the hyperparameters that in this representation forms that curve. And what the interpretability of that is, we don't know.
But as an example, suppose you have a set, just 3 variables, 3-dimensional space. You can take cuts in 2D and get a representation between 2 of those 3 variables. And that's not possible there. Cuts, so to take a cut, say, to take a reduction from 5 to 4 by taking some kind of cut.
Yeah, but then you need to take the reduction from 4 to 3 and then the reduction from 3 to 2.
And nothing is learned by doing that kind of exercise. Is that right?
We haven't tried that, to be honest. Right, Andrea?
Yeah, no, we haven't tried that.
There is a chat message by Tom Berger in the chat. Geoeffectiveness also depends on the Earth's magnetic field orientation relative to the Sun, which is optimal for reconnection with CMEs in March and September. That is Russell-Macpherson effect. Adding the date to the feature set might improve skill.
All right, okay. That's very useful. Yes, indeed. I guess adding the date would be even just a month, maybe.
We were not aware of this when we performed these experiments.
Michael, you have a question?
Yeah, I would like to know, this study you did an after-the-fact analysis of various characteristics that came with CMEs and their geo impact. How could this end in a predictive capability?
I'm sorry, and I'm not sure I got the question.
How could this approach end possibly in a predictive tool?
So ideally, before I started working on this project, I believed that we could have a model that would simply take in the data and correctly predict whether the CME will be geo-effective or not. Unfortunately, with solar onset numeric data only, we can see that while we can pretty accurately find the geo-effective events, we also get many false alarms. So the way I see my work having a practical application would be as an initial filter in a system. So we could filter the CMEs, and if it says geo-effective, then we would need to filter it once again and see whether it's a false alarm or not.
Okay, then you are arguing that if we could identify and find additional criteria, this tool might be coming up with less false positives.
Yes.
That would be a potential direction to go into. Yeah.
Yes.
I got it.
What Tom already suggested could be another data point to add to the model.
Yeah.
Another thing which Andrea mentioned would be to have the actual flare positions, but the flare catalog spanning 20 years was impossible to find. And we have in our paper some experiments on smaller periods where we had the flare catalogs, and that improves metrics by significantly. And especially if you have the flare catalog, you would know that if the flare is front side or backside. So you would remove the problem with backside halos, because this model with these metrics gives these reasonable results while also not being able to distinguish between front side and backside halo CME. So all of them are there. So there's enough way for improvement. And I think that with the paper, we also included a small notebook and a curated data set that anyone can use and play with.
Any other question? Paul?
Hi, yeah, nice talk. But so I have a question that is like, I guess it's about this approach in general, not necessarily the application to the geo-effectiveness. And I guess it kind of touches on what Michael was getting at, maybe. And I think, so my question is, how much is this just a tool to predict what you want it to predict? And what's the possibility of actually learning something physical with this approach? Because like machine learning always seems like a little bit of a black box to me, right? You give it the data and it spits out results, but you have no idea how it gets to the result. So how do you use this to learn about the physics of the system?
Thank you. That's a very good question. And it is true that indeed some models have a black box or are black boxes, the way artificial neural networks are. So maybe linear regression or logistic regression are less of a black box because we can understand the weights and understand that basically they give some importance to some features, for example, but indeed, explainability is an issue for these models. As a computer scientist, I'm mostly interested in making them work, so making the tool work, and its task is to predict accurately. But I can obviously see how explainability is of very much importance to researchers in the field. There is work being conducted for explainable AI in the ML community. For this particular project or any application in general, I guess I would say that through the process, you learn through the process of applying this machine learning techniques and trying to see what doesn't work and why it's not working, you learn some stuff. For example, the way we've learned here that given that it has so many false alarms, we've checked why that's the case, and we saw that they're all due to to full halo CMEs, and we could check that with the literature and see that okay, there is a consensus that these are the ones with the most geoeffective potential. And so I guess this can be used as a reinforcement of that, maybe. Or the fact that the machine has troubles distinguishing between these classes, and the fact that we see that there are very similar geoeffective and non-geoeffective samples makes us believe that these few features that we're using are not what makes a CME geoeffective, and there's something more to that and something more to explore. So, for example, this gave me the idea that if we looked at the images or videos of the CMEs, there probably is data there, for example, regarding the direction that's not embedded in this numerical data that might make a difference. I'm sorry if it was a very convoluted answer, but does this answer your question?
Yes, thank you. And I don't take any issue with you just trying to get it to work. I think there's value in that in and of itself, but I was just kind of wondering if we can take it further. But thank you.
I would also add that these UMAPs are the first step towards trying to explain something, because it's clear that that curve means something in that hyperparameter space. It's not a random distribution of points. At the moment, we wouldn't have an answer to it. And this whole UMAP was Andrea's idea, and she just came up with these plots, and we spent quite some time just looking at them and trying to figure out what's there. But we wouldn't have an answer. But this is the start of a path to try to get some meaningful physics out of it. As in, what's the exact combination of parameters that creates that curve out of the 5 that we used.
Yeah, I just want to add to this. Sorry if I haven't understood correctly, but in one of the previous slides, first UMAP with all types of outcomes, true negatives, false positives, and false negatives. Yeah, on that map, if you see a CME coming out, you just place it out. It's just placed on this map. You can tell right away if it's gonna be geoeffective or not, or it could be geoeffective, right? So I think this is pretty neat results in a way that as long as you understand the mapping, which must be encoded in the method, right? It's like some sort of minimization of dimensionality. That's hopefully it's a linear process. Because if it's not, then yeah, it's a bit more troublesome. But like this is a pretty powerful metric, right? Because like you just observe something, you put it on this map, and unless it's on that line down there, you know it's not effective, right? Do you understand this correctly, or?
I'm not sure I understand your question.
If I give you the 5 parameters of a CME, and you just
Yeah.
put it on that map, and if it's not down there in that region, it's very colored. it's pretty much 100% sure it's not going to be geoeffective.
But that's the model itself, not necessarily the map. I mean, if you feed a new CME to the model, it will tell you that it's not geoeffective pretty much, and that's because of the sample. It has 24,000 CMEs that it knows it's not geoeffective, so it's trained very well to say that something is not geoeffective. The problem is with those halo CMEs, the back halos, and all sorts of where those class overlaps, which is that dreaded curve. That's where the errors come from. And most of the false positives are actually back halos, and we have a little statistics in the paper about those. So, but yeah, to answer specifically your question, it's you don't even need to get to that point. You just run the Colab notebook that we have, and it will tell you yes or no. And if you want to add it specifically to a map to see it there, you can, but it's not. This wouldn't give you any more than what the direct output from the model gives you.
So let's recall what those 5 quantities were and at what time you would have them. At what time in the time development of an event.
Well, there, from what I remember from the CEDO catalog, and this is mine. Sorry, Andrea, for hijacking you, but
No, thank you. Please
my
do.
part. So these are all automatically calculated by CEDO, by them, and they're pretty much fits and averages over the CME's expansion over the LASCO field of view. So pretty much in those 1 to 2 hours until the CME goes out of the coronagraph field of view is the time range for these parameters. Unless it's something peculiarly slow, but those are there.
And when is this data available?
Well, if I remember correctly, if you use the fast telemetry data, it's a couple of hours. The definitive one comes slightly after that.
Okay.
But there's a 5th one that's not on there, which is some index.
Yes,
Yes.
there was a flare index from the.
And what about the availability of that? What does that come from?
That is, unfortunately, as I've said, it was computed up to 2015 only. I was unable to find the reason to explain that. However, the model performs reasonably well, so the differences are minor when including this flare index as well. So we could perhaps get results as good. That's an idea for a future experiment in which we could use these values only and train up to 2022, which is the most recent LASCO data. So remove this, but increase the number of samples. Yes, please. Sorry.
But the flare index then is not available in this window of time, or is it available in this window of time that you have the LASCO data so that you can predict? And
Yeah,
so it is.
it's available from 1996 to 2014. That's why we couldn't train it
That's not
today.
what I mean. Is SWIFC going to get the flare index in time to predict a storm at Earth? Is it like just as quick as the LASCO data, or is it computed a week later?
That I don't know.
Yeah, that's what we need to find out. What is Candley Observatory?
This is the official citation of the flare index. I have it linked in my paper, and basically it's obtained
The
from
flare
NOAA.
index comes first, right? Normally,
Yeah,
it
okay.
goes, and that comes first before they.
Yeah.
That normally is pretty quickly depending on flux, but I'm not sure how they did it, but.
We've also I just found out from the Bulgarian observatory that they have 20 years of flare catalog that spans for 20 years. And if they do have CME associations, so if we could use that, but I haven't checked yet exactly what's their temporal range and so on. And we can plug it in, that would also be a powerful tool, but it requires quite a lot of manual labor to match the CMEs with the flares and everything. Because if you have flare positions plus flare strength, maybe other derived flare indexes if they work or not. But these are the three, this will make something like this work instantly, I would say. And the flare parameters can be computed on spot. It's pretty much near real time, I would say.
I'm surprised that, so mass is not included inside the LASCO data set.
Not for all.
There's very few events where the mass is computed, and then the machine learning algorithm doesn't like empty boxes. It needs to have a value, and if you put mass 0, then it will start spewing out nonsense. So we had to restrict the catalog to only the columns that had enough complete values.
Exactly.
So all of our 5 data points are complete for all of the 24,000 CMEs. Right, Andrea?
Yep, that's correct.
So how is flare index defined?
They compute something like a daily average of flares across the entire disk. And they made some form of index out of it. And it has a smoothing component, so it's not the raw number of flares. It's
So that's different from, I thought maybe it was something like, the M class, X class. So it's not that. It's some
no.
daily average.
So it's
Yeah.
more like an activity index.
It's more like an activity index rather than a flare strength index. Again, we used one catalog for a subset, but we didn't have, and there are some experiments run on the Yashiro has a flare catalog, and it has flare to CME associations, but there's the time period was too small to include in the final model. We just left it as a small side experiment of how well could we improve things if we include flare data, and the answer to that small experiment was a lot. But we don't have that data for large for the large temporal intervals.
But the input data for the flare index in these years before was also taken from space assets.
I don't think so. I think it's their internal. They did it internally. I mean, I'll have to check up the documentation for it. I don't remember it by mind, sorry. But it's something they computed in-house. I don't remember exactly what were all the input data sources for it.
Because, I mean, in solar data, there must be some way of extracting an average flare activity over time with a certain accuracy given the resolution of the various telescopes that are on there. And that would be an at least uninterrupted measure. So I would be curious what exact input data these folks were using.
I'll try to send you the documentation for it.
Because, I mean, the guys at the Space Weather Forecasting Center, I think in some way recognize any flare that's going on.
Yeah, the problem was that we couldn't include something like a full GOES flare list, and it's not even properly labeled. So it's not it's not something that you can uniquely identify. That's the problem. You need to go and do things manually. Because we should have the flare numbers daily from GOES for the entire period. But it's not an easy way to quantify those.
Yeah, but in going forward, I would then argue there should be a way of defining a recipe to extract out of the data that is streaming in this kind of a flare index and having that available in some time delay to yet to be determined. But it can be days. So I mean, it's to me it sounds that was so far sort of a considered a side battle pursued by some groups, but if that is now a criterion that would really sharpen an approach like this, then maybe one can add that to the standard extraction of the information flux from these assets that look at the sun all the time.
That might work. There's, for example, there are some automated catalogs that you can query from but they only started with SDO, so they started in 2011. So then we lose our 200 geoeffective CMEs. We're going to be left with 50 or 70 or that's too few to actually train anything.
This might be a viewpoint, but I wonder if you thought about going back and recalculating some of this kinetic energy and mass. You have the volume maybe for the back. I know it's a lot, but if you're doing it automatically, just from the parameters that you have, maybe that'll give you some more info. You might be able to distinguish between a backside and front side CME just from like keep the kinetic energy at,
But
whatever.
the problem is that the error bars in those go bad directly proportional to how halo the CME is. So that's a problem. And if they couldn't calculate it automatically, it means it's quite hard to get anything that's meaningful compared to the error, because that was their criteria. Because they do their documentation says that they do get a number for all of them. It's just that they don't want to output it.
Okay. And if it's calculated from these other parameters, it's not strictly speaking new information, right?
Sorry?
If it's calculated from these other parameters you have there, then it's not strictly speaking new information.
It would be more than just the angular widths or accelerations or linear speeds. But that's what Andrea was saying, that we might be able to employ a computer vision model on the entire LASCO data set and train a model that can distinguish by itself using the raw images without relying on calculated parameters. But that's a big project by itself.
But maybe just to answer that exact question, like if you see, that's the reason why we're not using, this other variable. So yes, these are computed based on this data. So we have the information already. My understanding is, please correct me if I'm wrong, that these are standalone. They're not only computed based on this one. So this would be new info. It's just not available.
And there might be repeated information between the mass and the kinetic energy. So pretty much you use a polarized brightness measurement of the entire CME after you isolate it with a threshold. And then using polarized brightness, you might get an estimate of the density in volume mass, and then mass to kinetic energy using the speed. So kinetic energy might not be an independent parameter, but mass surely is.
I stopped.
Thank you.
Thank you, Andrea.
Thank you.
Again.